we want to imagine that there's a gravity switch here. We have a really cool physics lab where we can hit this gravity switch and gravity shuts off in the physics lab, and we can do all sorts of cool things where we flip and do martial arts exercises, and I could let go of this marker and it would just sit there. And if I fired a gun at 5 meters per second, where would it be 1 second later? It's going to keep going to the side. How many meters to the right would it be at time 1 second? 5 meters. So I'm going to just kind of sketch that in and say, hey, at 1 second, it's going to be 5 meters from where we started from. And how about at 2 seconds? Yeah, it'll be 10 meters from where I started from, or I could say an additional 5 meters. And this is the point, right? This pattern continues. Every 5 seconds it moves, every second it moves 5 meters to the right. And that's because it's not accelerated in the side-to-side direction. Even if gravity was on in this case, which it's not, gravity's not pulling it to the side, it's only pulling it up and down. Now we're going to come back over here and we're going to switch the gravity back on. And imagine for a second that we had a second ball that we let go from the same place that I'll draw in blue. How far will it be after 1 second? Another way of me asking this question is, what if I took this marker and we had no air resistance in the problem and I just dropped the marker and it was free to fall as far down as it wanted? How far would it be after 1 second? I'm going to give you guys 1 minute to figure this out. See if you can answer that question. Where will the marker be after 1 second? You guys can work in groups, talk to each other, see if you can figure it out.
This is the important part. This is the important stuff behind trebuchet physics. I mean, I have all the other things that I wish I could go
Yeah, assuming it's dropping after 1 second. Well, assuming the point drops.
Anybody have an answer yet? Sorry? On the ground? So so one of the caveats is it says free, it can fall as far as it needs to. In other words, maybe I'm hanging my hand over the side of a very tall building. How far would it be, Alex?
4.9 meters.
Good. So 4.9, if we're using 9.8, let's talk about where that comes from. That's the right answer. The initial y component of velocity, notice how I wrote that. This is the same first Galilean equation that we saw a week or two ago, except now I'm putting the subscript of y, meaning we're only dealing with things going up and down now. Even though this ball might be going to the right at 5 meters per second, its initial y component of velocity is 0. It's not going up and down at all. So I'm going to say that that is 0, and I'm left with delta y is equal to 1/2 at squared. And now I can answer the question. I'm going to plug in, instead of 9.8, which is the more accurate number, I'm going to just plug in -10 to make it mathematically a little bit easier for me. And I'm going to leave the units out. And so we can see then that after 1 second, I'm going to be at -5 meters of vertical displacement. And Alex said 9.8, but that was using, said 4.9, but that would be using 9.8. So that means that if we let go of the ball, it's going to be, after 1 second, about 5 meters down. How far will it be after 2 seconds? Will it be another 5 meters below that? Or will it be smaller or larger? It's going to be a bigger number, right? It's not starting from rest anymore. We would change this number from 1 to 2. So let's do the whole test again and say, okay, what's the vertical displacement after 2 seconds if we drop it from rest? Well, after 2 seconds, 1/2 of -10 is still -5 times 4 is -20. So now it's going to be way lower. After 2 seconds, it's 20 meters down. Now clearly on the sketch it would hit the ground, but how far would it have fallen if it could after 3 seconds? Good, 45 meters, right? So it just keeps getting bigger and bigger. The spacing in between all of these things gets larger because the velocity keeps increasing. So this black sketch is what the ball would have done if it had rolled off this end of this cliff without gravity. The blue sketch shows what would happen if we ignored the side-to-side motion. We know that our answer is not either one of those. It's the marriage of the two, the horizontal and the vertical. It's a parabola. After 1 second, the real location of the ball is there, 5 meters over and 5 meters down. After 2 seconds, the ball is 10 meters over, but 20 meters down. And this is going to give us a trajectory that should be familiar. Most of us have thrown something before. We know that it's going to curve in the air. And that the longer it's in the air, the more downwardly curved, or the more downward the direction of its velocity is. So this kind of conceptual analysis that we've just done here is consistent, or should be consistent, with what you guys have done. So now we're going to algebraically attack this problem, and I'm going to give you what I think is a strategy for solving this kind of a problem. It's called a horizontally fired projectile. That means that its initial y component of velocity is 0. So I'm going to kind of label this problem horizontally fired projectile. And what I recommend is that you have 2 sections on your paper. The section to deal with all of the motion in the horizontal direction, or the x direction, and you physically separate it, I use the squiggly line, from anything that's happening in the y direction or the vertical direction. So before I even get started, I want to remind myself that in the horizontal direction, the object is non-accelerated. That's because gravity is only accelerating the ball down. We're doing these problems in the absence of air resistance. Air resistance is an accelerating force, but we're ignoring it. And at low speeds, it's normal to ignore air resistance. Of course, if I were driving down London Bridge Road and it's a nice day like it is today and I stick my hand out of the window, there's a little bit of air resistance. But it's very, very velocity dependent, right? If I go really fast, then I can start to really feel it. But at low speeds, you can almost ignore it. And in the vertical direction, I'm accelerating. So A is not equal to 0 in the vertical direction. A is equal to 0 here. If I'm non-accelerated, there's really only one model for motion, and that is velocity is equal to displacement over time. And I'm going to put a little subscript of x next to velocity. Don't let any of the notation intimidate you. This is just saying, hey, remember, man, that we're not talking about how fast it's going up and down. We're only talking about how fast it's going in the sideways direction. But nothing has changed. We're just using a few extra subscripts to make sure that that's cleaned up. And in the accelerated motion, I'm just going to write down, in the accelerated plane, I'm going to write down the first Galilean equation. Delta y is equal to VOYT plus 1/2 AT squared. Most of these problems set up like this, where you're using this constant motion model that's just standard definition for velocity, and then the first kinematics equation. And so what do I know in the problem? Well, I was given the initial velocity. The x velocity is 5 meters per second if I'm only using one sig fig. I don't know the displacement. That's really what I'm trying to solve for. How far from the base of the kind of cliff does it land? Now, in order to solve a problem like this, we would need one piece of additional information, and that is, how high is this cliff? Let's imagine that it's 25 meters tall from the top of the cliff to the bottom. We also don't know the time. And here is the problem. If we knew the time, then we can easily answer delta x. We just algebraically solve for delta x. We multiply velocity by time, problem done. If that's what they're asking us, we can easily do it if we know the time. But we don't. So we have to go over here. And we have to answer the question, if I just dropped this thing from 25 meters, how long would it be in the air for? How many seconds would it be in the air for? And once we know that, we're going to take that time and plug it back in over here and get our answer for horizontal displacement, or what is also known as range. So let's solve this formula for time, given that the initial y component of velocity is 0. If I were to kind of write out my initial conditions, we know the acceleration is negative 9.8 meters per second. We're looking for the time, and we know that the vertical displacement, delta y, is negative 25 meters because that's the height of the cliff. It was given to us in the problem. I want you guys first to algebraically solve this expression for time, and then when you're done, plug in the numbers and get the total amount of time that that projectile was in the air. I'm going to give you guys 2 minutes to do that.
Oh, you know that's because it's got right? So it took 2 seconds to do it here, definitely just over 2, I'm guessing like 2.1. So that sounds like crazy. Sounds good. Thanks, Nick.
Okay, there's a sig fig question here, but for now, let's focus on the kinematics algebraic rearrangement. We have the first equation of motion. We're solving it for t. This middle term is 0. Because the initial y component of velocity is 0, this entire term goes away. I multiply both sides by 2. I then divide by a, and then I take the square root of both sides. Are there any questions how I got to here? Okay, then I plug the numbers in, and I get just about 2.2 to 2.3 seconds of time that it's in the air, which seems to be in line with what we were doing earlier. We said it'd fall 5 meters in 1 second, 20 meters in 2 seconds. So that means 25 meters should be a little over 2 seconds, and that seems right to us. Are there questions on how we got that number, 2.25 or so? Remember that this is an intermediate step. I do not have to truncate for sig figs here. I only have to do that in my answer. Now that I know the time and I know the velocity, I can easily solve for horizontal displacement by multiplying velocity by time, and I get around 11 meters. Now, if my initial velocity was only given to me with 1 sig fig, I would have to round that down to 10. If there were 2 sig figs, then I would round, then 11 would be okay. So in this case, I think I only gave that 1 sig fig. I think a better answer now would be 10 meters of range because I only had 1 sig fig. Are there questions on what we did here? This is the kind of focus of the entire class for today. So if there's any uncertainty, this would be a great time to ask. Okay, I'd like to give you guys a short follow-up question that you guys will work on in teams. I'm not going to help you. I will kind of solve it at the very end here. But imagine that we have a car, and the car is driving in Wyndham, and the car is near this kind of bog area, and it drives off the road, it goes through the barrier, and lands into the bog. Now, nobody's hurt, but it goes through the bog, lands on the ground here, and we're going to say that this is 36 meters away from the base of the cliff, and we're going to say that the cliff is 12 meters high. So, the driver of the car says, I think I'm going to sue the town of Wyndham, and the reason is the barrier did not restrain me on the road, and so therefore the town is responsible for this unsafe road condition, and they're liable for all the damages and medical costs and things like that. The town comes back and says, no way. There's a posted speed limit right here that says 16 meters per second is the maximum speed on the road. Now, nowhere on Earth are speed limits posted in meters per second. Most of the world uses kilometers per hour. We're in miles per hour. Let's just imagine that in our utopia, speed limits are posted in meters per second. So the question I have is, suddenly you get a phone call from one of the lawyers in town, and they say, hey, listen, we've got this whole court thing, we've got to show that in fact, the driver of the car, after breaking through the barrier, was still going faster than the posted speed limit. We can't make our roads safe for a 3-ton cement truck barreling through at 80 miles an hour. Like that would be just unrealistic. So we're not liable because the driver was breaking the law when they were operating the vehicle at those speeds. So my question to you is, who's right? Who's going to pay for the damages here? You guys understand the question? Ready to go.
So
You sure you don't know the acceleration of the car? Still right, right?
No, not vertically, it's vertically.
Right, it's not accelerated, right?
So we know about height, now we know how far we go. Yeah, so we know about height.
Yeah.
That's
we're
what's
not
going
looking at it.
Well, yeah, we know.
Nothing else. We know delta line, we know what acceleration is.
In order to find time, we're getting the same stuff as well, because that's what we're getting.
Velocity of y.
We don't know.
Zero acceleration.
2 delta over of course, all that.
V naught is where like you're starting at the top of the delta y.
36 meters.
But you're not accelerating it, so
I just want to make sure the passes. Yeah, I got you.
And what you do is you just plug in the value, so it's 2 times negative 12, which is negative 24 over negative 1. There's 12 is the place of delta, because that's the total distance. They're all negative.
24, negative 24,
No, 16 is the speed. I did 36 because that's the well, we're looking for time. That's what we got to do. We have delta x. We have delta. What we need to find is time, so that we can speed. That's the speed. If it's below that, then it's 10 below that. Okay, yeah, that's a good word.
Oh, I have it. Oh. I haven't like gone.
That's what I forgot.
Okay, this problem was only slightly different from the one we kind of started with. The difference is we again started here in the horizontal direction, but we don't know not only time, but we don't know velocity. We know delta x instead. We can't go anywhere with this. We want to know the velocity, but there are too many unknowns. We only know this, we don't know time. So we have to go get the time from the vertical analysis. We again solve this problem for time algebraically, and when we plug our numbers in, we get about 1.5 seconds. Are there any questions on how we got about 1.5 seconds for the falling time of the car to the ground? Take that time once we have it, we bring it across over here and we say, okay, listen, the car is going to keep going at however fast it was going for eternity. The problem is gravity pulls it down to the earth and it runs out of time. If I am out in deep space and there are no gas particles nearby, no atmosphere, no air, and I take this tennis ball and I chuck it at 5 meters per second to your right, it'll keep going for 5 meters per second forever, for eternity. I'll be long gone. You guys will be adults. You'll have your own families if you choose to do that. You'll die. The next generation will live. And the stupid tennis ball that I threw like 80 years ago will still be going to the right at 5 meters per second. The difference is on Earth, gravity pulls it down and it hits the Earth, it runs out of time. And so that's really what we're solving for right here, 1.56 seconds. It only gets to go to the right at whatever speed it's going for 1.56 seconds before gravity finishes the job and it hits the ground. And we get initial speed of 23 meters per second. We can now answer the question whether the guy was speeding or not. He broke not only, probably going faster before he broke through the barrier, and then by the time he left the platform, was still exceeding the speed limit. I don't think the town is going to pay. Are there questions on this problem? Okay. Your homework, by the way,